Hello, how are you? My name's Christopher, and it is a privilege to be here. No, really, I'm a 6'3", straight, white, cis male, born in Australia. The privilege is all mine. I'm a chemist, and when I tell people this, they usually ask 3 questions. So to get it over with, no, not all chemicals are bad. No, I don't work at Chemist Warehouse. And no, I can't give you a discount on math. My prices are already rock bottom. I'm a research chemist working at the University of Sydney. So I work in a laboratory, which means my mum thinks I spend my days doing this, my friends think I do this, but in reality, it's mostly this. Now, I am really interested in trying to find new ways to make certain chemicals that we need for society to continue, but doing so in a sustainable way. So less energy, less waste, and less greenhouse gas emissions. Now, the chemical that I'm currently focusing on is called ammonia. It's a happy little molecule made up of 1 nitrogen in blue and 3 hydrogens in orange. And you might be thinking, who cares about ammonia? What's it got to do with me? Well, it's actually all around us in our daily lives. It's got a strong, pungent smell. So if you've ever used window cleaner, that's ammonia. It's a key ingredient in smelling salts that they use to wake people up who have fainted. And if you leave urine to go stale, it produces ammonia. So if you're not sure if you've smelt it, the toilets are over there. So the uses of ammonia can be remembered with the 3 Fs. It is a really good fertilizer, so we use it worldwide to grow our crops to feed our population. In fact, if over half the world's population rely on us making ammonia synthetically in an industrial process. So just think of that. Half the people alive today could not be alive if we only had natural ammonia. It's also useful as a fuel, so it's a high energy molecule, and we can use it in place of petroleum in our transport and our energy storage. And thirdly, it's good for freaking big bombs. So ammonia is a high energy molecule, and it can be mixed with nitrate and you make explosives. So hopefully I've convinced you ammonia is good. For the first 2. Pay attention. So ammonia is good, but we haven't had a good way to make it for a long time. We relied on natural sources. And that's primarily in the form of guano, which is bat droppings, which has urine in there. That is until the 1910s, when 2 German chemists, Fritz Haber and Karl Bosch, were tasked with making ammonia in an industrial process. And so they wanted to make Germany self-sufficient. They wanted to feed their population, drive their vehicles, and invade their neighbors. So the politics aside, the science that they came up with is brilliant. It's so brilliant that just after World War I, Fritz Haber won the 1918 Nobel Prize in Chemistry for the synthesis of ammonia from its elements. I guess the selection committee, amongst all the scientific furor, they did not see a problem with that. So what they came up with is to take the constituent parts of ammonia, so the nitrogen and the hydrogen in their pure gas forms, and put them in a reactor. Now these don't really want to do anything, so they have to give some heat energy, and they heat up the reactor, and also add in a special material that we call a catalyst, so that they make the reaction go. So they add nitrogen and hydrogen, and they heat it up so it gets all hot and all bothered, high pressure, and then the nitrogen and the hydrogen, they get a bit excited, they do a wiggle, they come together, and then they get their baby, ammonia. So this process is really good, and it's done on a really big scale. So this is the first reactor from 1913. So for size scale, that's me, there's a little man down there, so shrink me down. This reactor is about 6 privileged white men tall. That's in metric. I wasn't sure how to convert it to imperialism. these reactors are great, but over the years we've just built bigger plants with bigger reactors. So this is 1954, and then this one, oh actually that's a mistake, that was quite recent, built in Western Australia. Fundamentally, over the last 100 years, we have not changed the technology. We just keep making these plants bigger and bigger. So what I want to do is take a completely different approach. Now, the Haber-Bosch process is pretty energy efficient. It uses up a lot of energy. It's about 2% of the world's energy use per year, but it creates a lot of ammonia, which feeds half the population. A big problem, though, is the source of the hydrogen. So we currently get that by a process called steam methane reforming. So steam means water, methane is a fossil fuel, so it's a non-renewable resource. And in another reactor, they mix methane and water, do steam methane reforming, and get this hydrogen that they want for the Haber-Bosch process. As a byproduct, they make carbon dioxide, which is a greenhouse gas. So that's not very good. What I want to do is see if I can do the same process, but without the methane, and without doing it at high temperature and high pressure, so I can cool the reactor down and have it at regular temperature. And then, in place of pure hydrogen, I want to do it with water. So water still has those two hydrogens you need to make the ammonia. So I'm trying to take nitrogen from the air and water, combine them together, and then use renewable electricity and some of the special materials, the catalysts, that make this process happen. So I think this is much better because the byproduct is not CO2, but rather oxygen, which is good. Yeah. So my research focuses on trying to work out which special materials I can use to use that renewable electricity to make the ammonia. Now, I've taken inspiration from Mother Nature. So plant roots, some plants have enzymes inside them that do exactly what we want. They take nitrogen and water and they convert it into ammonia at room temperature and room pressure. Regular pressure. Freebie joke, great. So taking inspiration from what nature's worked out over the billions of years of evolution, I'm making materials that are very similar to the active part of those enzymes, and then I can make them in the lab. This is great, but I first need to test them. So the industrial reactors are just a little bit big to fit in a lab, so I have to find a way that I can shrink this down into my lab. And so to do that, I use a process called 3D printing and make a little reactor that I have designed, and then that lets me test all of my special materials in these little reactors. So I'm currently testing a range of materials in these little, wrong pocket, little reactors that are just this big, and they're quite cheap. They cost about $2, so it's really helping test lots of materials all at once. And I'm pretty proud with having come up with this reactor, and so part of the work is just trying to get this out there so that other researchers can test their special materials, their catalysts, and not just for making ammonia, it can be used for making a variety of chemicals. I'm also really excited because I think I have made ammonia in the lab. Obviously I need to do some more work and get the catalyst just right before it can be rolled out in the big industrial scale that we need. But if you remember nothing else about me, remember I'm working on a magical science reactor in which I take this really big polluting Haber-Bosch ammonia producing plant and I shrink it down into something that fits into my hand. So this will be really good because I'll make ammonia, and doing this I can use nitrogen from the air and water from the air and then just electricity from a photovoltaic or a solar panel. And so I can produce fertilizer on a farm or fuels at the station rather than having them out in Western Australia or having to travel far away. So thank you, my name is Christopher. As a reminder, I'm a chemist. However, you won't find me behind the counter at Chemist Warehouse. I'm out the back selling meth.